Good morning, ladies and gentlemen. We are Team String Theory, and we're here to present our final project for your perusal.
For the question generation component of our project, we used a template-based approach. What this means is that we had generic sentence structures that we expected to see in a Wikipedia article and used a regular expression-based algorithm to find sentences that match this sentence template. Our templates could then be arranged in predictable ways to create questions. An example of a basic template that we used is A is B, which can be arranged into a question of the form, is A B? So say the article had the sentence, Alan W. Black is a Scottish professor of computer science. This sentence would match the A is B template and be arranged to create the question, is Alan W. Black a Scottish professor of computer science? Even with a small number of sentence templates, a typical Wikipedia article will have many sentences that match at least one of our templates. This resulted in a large number of questions, some of them being nonsensical. Our next step was then to filter out these bad questions. Looking at the questions our system was generating, there were many common errors we saw that we used to create this filter. For example, we created a set of bad bigrams that commonly occurred and always led to ungrammatical sentences, and eliminated any questions containing these bigrams. A few other features our filter checked were ambiguous pronouns, question length, comma count, and mismatched parentheses. After the filtering step, we processed our questions to make them appear a little bit more natural and human-like. This involved things like fixing capitalization and removing unnecessary whitespace. Our system had a few other features, with some that ended up being cut from the final project. One example was the blip parser, which we used to create parse trees of our questions, and tried ranking them by an evaluation score based off of a PCFG. However, this slowed down our system, and the results of the ranking didn't create too much of an improvement, so we decided to strip it. We also had fallback methods, if it were ever the case that our system couldn't produce the desired number of questions. Our first fallback was to use a regular expression to find the dates from the article and ask about the importance of that date with respect to the article title. We also used part-of-speech tagging to identify pronouns in the article and then asked about their relationship to the article title.
The answering system is divided into two main components, finding the best matching sentence, then post-processing to extract the relevant answer. To extract the best matching sentence, we used a noisy channel model, where the Wikipedia article is the source data and the generated questions are the scrambled data. The noisy channel itself is other groups asking systems. Our job was to go from the questions back to the Wikipedia article and find the most relevant sentence. To do that, we first used the Stanford parser to extract a set of relevant features from the question and the Wikipedia sentences. The features we used are word overlap, which includes both unigram and bigrams, question length, which compared the question length to the original sentence length, positioning, as in the position in the article of the sentence, named entities, both overlap and existence, synonym overlap, and part-of-speech overlap. From training, we found that the best features were the unigram, bigram, word overlap, named entities, and part-of-speech overlap. Interestingly, the positioning in the article was also a good predictor as well, because it is much more likely that the question is generated from an earlier sentence than a later one. We put all these features into a vector and used logistic regression to learn a model from the training data. The training data we used was around 1,000 questions, which we hand-labeled and curated. To cross-verify our data to prevent overfitting, we held out around 30% of the data to perform testing and trained on the other 70% of the data. After training a model, our system would be able to find the correct sentence with around 72 to 73% accuracy.
For post-processing, we first tried to extract a succinct answer from the most relevant sentence. We used a parse tree to look for the canonical structure for each question type. Using a parse tree allows us to accurately determine the question type, even if there are clauses with a different question word. For example, the question, when Obama was in Beijing, who did he meet, would be correctly identified as a who question instead of a when question. To extract the answer for yes-no questions, for example, is Alan Black known for his research in speech synthesis? There will typically be three top-level components: the verb, is, the noun phrase Alan Black, the verb phrase known for his research in speech synthesis. If we find that the most relevant sentence follows a structure where the noun phrase is a subject and the verb phrase combines to form a new verb phrase, then we know for sure that the answer is yes. For who questions, if the most relevant sentence can be constructed by replacing the question word who with a noun phrase, then we know for sure that a noun phrase is the answer. We consider similar structures for passive sentences and to answer when questions. If we cannot find a matching, we just return the most relevant sentence directly. The second step in post-processing is to do pronoun resolution. We do this using code reference information contained in the XML returned by the Stanford parser. If the subject of our answer is a pronoun, for example he, we look for the particular mention in the list of code references and return the representative mention, which is what the pronoun is referencing. Finally, we try to beautify the answer. We check to see if the characters in the parentheses are printable. If they are, we keep the parens. If they aren't, they're usually phonetics and we discard them. And we get rid of spaces before punctuations and do capitalization.
Well, that's all for today, folks. Thanks for listening. Bye.